Okay, we are live now. So I welcome everyone on this very nice afternoon for another session of the NSF Wednesday Colloquium. And it's a great pleasure that I have just the former director, Professor Sandip Trivedi, giving his colloquium after maybe a few years after taking over the directorship and coming out of it. So Sandip, welcome. I would, for people who are hearing us for the first time and you have subscribed to the TIFR Platinum Jubilee events channel, the Wednesday Colloquium actually is the oldest scientific forum for the Institute. And it has been a place where we have invited international experts and world-renowned scientists to speak about the contemporary disciplines in physics, chemistry, and biology, disciplines spanning all the way from as small as an atom to all the way up to the big universe. So it's a really cross-disciplinary forum, and every time the speaker tries to connect to all the scientists across, from a young student to the faculty member of this institute, and tries to convey the excitement of science. So thank you, Professor Sandip Trivedi, for joining us for this session. So before I actually let Sandip speak, I would like to briefly give a little bit of an introduction, simply because I haven't introduced an ex-director before, so I would like to do it. So although he's all part of the community and within TIFR, he needs no introduction, but just for people and students in chemistry and biology, Sandip has been a theoretical physicist ever since he has joined the institute, and even before. He actually is a string theorist, and something that I guess chemists and biologists don't always listen to or understand, but it has deep-rooted implications in explaining, for example, expansion of the universe. His, of course, research interest beyond string theory is cosmology and particle physics, and he completed basically his master's degree from IIT Kanpur and did a PhD from Caltech with Professor John Preskill, and then moved on to the IAS at Princeton, Wheeler Avenue, right, Sandip, and did his postdoctoral work there, which he finished by 1992. Sandip actually, because of his very, very well-renowned work in string theory, has won the Shanti Swarup Bhatnagar Prize, the Infosys Prize, and the TWAS Prize, which is the World Academy of Sciences Prize. Apart from this, Sandip has now actively had involved himself in administration and just served as a director. So Sandip, without further ado, I welcome you to give this colloquium on the entanglement frontier. Thank you, Sandip.
Thank you very much, Jyotishman. You can hear me, I hope? Okay.
Yes.
Thank you. Thank you so much, Jyotishman, for that very kind introduction and for the invitation to speak in this very important colloquium series in our 75th year of celebration. It's always a great privilege and honor to speak in the NSF colloquium, and I'm very happy to do so this time around as well. The title of my talk, as Jyotishman said, is The Entanglement Frontier. I would like to discuss a new kind of frontier in science which is emerging. This frontier does not pertain to the very small, deep within the atom. It does not pertain to the very large, distances way beyond our galaxy, or even to the very many atoms, many molecules, or many neurons, when we know new phenomena can emerge. Instead, this frontier pertains to our growing understanding of quantum mechanics, its true meaning and significance. And since quantum mechanics provides the bedrock of our understanding of science, as this understanding is growing, the new frontier promises to have important implications for many branches of science. Physics, of course, very widely, but also chemistry, many aspects of computer science, and other aspects of engineering, and also some parts of mathematics. I've been very excited about these developments. Well, here is a cartoon, a Venn diagram, as we are taught in school. Many intersections, but in the center, the quantum frontier. Now, I've been very excited about these developments, and they have begun to intersect also with my own research in ways which I would not have anticipated, certainly a decade ago. And I find these connections with these developments increasingly coming into my own work. So I've thought, let me give this colloquium trying to convey some of that excitement and my own research within the broader context of these developments today. But while doing so, I also want to convey a wider point, which I really do believe that the coming few decades, I think, are going to see tremendously exciting progress in this area. And this is a wonderful opportunity, I believe, especially for TIFR, to make big contributions. This is exactly the kind of role I think our institution can play when there's a new area in science to take a leadership role, both for the country and internationally. And I think we have that opportunity in this general area that I'll tell you about today. It's also a wonderful area for a young graduate student beginning their careers to try and jump in. I think there'll be many developments and lots of opportunities to make important contributions. I'll come back to this point about TIFR towards the very end. Mostly this is a science talk, but since Jyotishman mentioned it, I will lapse a little bit into my previous role just at the end for a transparency or two. Okay, so here's the rest of the outline for my talk. I'll begin by telling you or reminding you about some of the essential weirdness of quantum mechanics. Some of this is captured by Bell's remarkable work summarized in Bell's theorem, which is closely connected to this idea of entanglement that I will then introduce. Then in the second part of the talk, I will turn to exploring this concept of entanglement, tell you why it is so important if we are to build quantum computers which work in a way very different from the ones from the way our current classical computers work, with the hope of much greater computing power. Why entanglement will have to play an important role for that to succeed, why quantum computers might be so promising, and then turn to how entanglement entropy in turn is beginning to shed light, in a sense, on our general understanding of physics by telling you how one can try to quantify it, what that teaches us about the kind of structures, for example, gauge theories, which underlie our understanding of the fundamental forces of nature, as well as a lot of condensed matter physics. This is my own work in part B, along with my students. And tell you about how an understanding of entanglement is also allowing us to understand various aspects of condensed matter physics by teaching us how to classify phases of matter which we could not have classified in more conventional ways. So that will be a taste of just where all this subject is going, how it's connecting to computer science, to fundamental physics, to condensed matter physics, and so on. And then we'll end with conclusions. And then, as I said, a brief postscript of 1 or 2 slides about where we could go as an institution. Okay, Now, it might seem strange at first that there is this renewed excitement in understanding quantum mechanics and its implications. After all, quantum mechanics has been around for a while. It's about a century old. Haven't we understood it completely by now? Well, the quantum world is really strange. It's very different from the classical world from which we draw our usual intuition and understanding. And for that reason, it's taken a long time to truly come to grips with it. And we are only slowly doing so even today. But as we do so, it's proving to be a very rewarding and enriching experience. Now, here's Niels Bohr, as you know, one of the father figures of quantum mechanics, certainly thought about it very deeply, understood it very well. But even he, and this is in 1952, so it's nowhere near where quantum mechanics was first developed. Several decades after that, here he is also expressing the fact that it's a subject hard to understand. He says, for those who are not shocked when they first come across quantum theory, could not have possibly understood it. It is something not easy to grasp. Here's Richard Feynman, someone again who made remarkable contributions to the subject and also to quantum computing, and I'll come back to that in the talk. Feynman, of course, much more direct. I think I can safely say that nobody understands quantum mechanics. I don't understand quantum mechanics, ergo nobody understands quantum mechanics. Okay, in his inimitable style. Well, those were two of the leading thinkers of the past century. One of the reasons why quantum mechanics is difficult to understand is that the quantum world is intrinsically probabilistic. We all know this because of the Heisenberg principle. You can't measure both position and velocity. There has to be some uncertainty. But in fact, it's even more subtle. One has to work with probability amplitudes, not even probabilities. Add those probability amplitudes and then take their mod square to obtain probabilities. There is really no analog of this in our day-to-day experience. You know, we do grapple with probabilities in our day-to-day lives. I hope there is a very low probability that I contract COVID in the future. I certainly hope that's true for you, right? And so on. But probability amplitudes, well, nothing equips us in our experiences for that. The underlying description in quantum mechanics, as you all know, is in terms of a wave function. And think of it as a wave, like a water wave, except it's a probability amplitude wave. As the system evolves, waves, the probability amplitude coming from different paths interfere with each other, more like water waves interfere. And then you have to take the analog of the total power in the water wave by taking the sum of all the paths and the probability amplitudes from them, and then taking a square of that. That's how you compute the probabilities in quantum mechanics. Very strange, but something we all learn about and make peace with after our first course in quantum mechanics. But that's not to say we truly, really understand what it is. Okay, this aspect of quantum mechanics is beautifully summarized in the double slit experiment. I think everyone who does a first course in quantum mechanics learns about this experiment. Here I've tried to summarize it. I took this picture from ResearchGate. There's an electron gun. That electron gun fires one electron at a time. So the different electrons don't interfere with each other. One electron comes out at a time, goes through the screen, which has two holes in it, 1 and 2. And finally, the electron ends up on this backstop where you measure where it hits. Now, if you close the second hole, then what you get is the curve P1 for the electrons going through. Not surprisingly, it is peaked where the first hole is located. Okay, so this gives you, if you like, the probability to find electrons if only the first hole is open. If you close the first hole, open the second, you get the curve P2, now not surprisingly peaked, where the second hole is open. Open both holes now. Only one electron is going through at a time. But amazingly, what you get is this interference pattern. It is not the sum of the two probability distributions if the electron, excuse me, one or the other hole was open alone. It is something very different. And in fact, it is peaked where there is no hole at all, at the center between the two holes, where there is a blockage. This is because the probability amplitudes go through both holes, then interfere to give you the net probability after you take an absolute value square. So this shows you that it's really like waves interfering. Okay, this has been measured in many, many experiments. We know it is true. It is the way the quantum world works. You take the mod square of the wave function. Okay, so this is one very counterintuitive aspect of quantum mechanics. In classical mechanics, of course, it's much different. You assign a definite position, a definite momentum to any particle, you follow it. If you have a bunch of particles, you do that for each one of them. That is not allowed in quantum mechanics, as I said, because of the Heisenberg principle of uncertainty. There is an irremovable uncertainty either in X or in P or in both, depending on how you set up the system or what measurement you carry out, which is set by h bar Planck's constant. Okay, so this aspect we know about, although as I said, it's hard to always, wrap your head around it. But there is a second, also very strange aspect of quantum mechanics. This is at the heart of the more recent developments, and it is at the heart of my talk today. And it is called entanglement. The wave function which describes a system is often non-local, cannot be described in a local manner. I'll explain what I mean by that. Even though all consequences in quantum mechanics are local. What do I mean by that? You cannot send a signal instantaneously from one point to another, even in the quantum world. But if you try to describe suitably set up systems in a quantum world, you have to describe them in a non-local manner. A consequence of this is that quantum systems have non-local correlations which have no classical analog. It's these non-local correlations which are referred to as entanglement. And this is the second facet of quantum mechanics, very different from the classical world, which adds to its strangeness and weirdness. And as we have slowly begun to understand it, now is responsible for some of the power that a quantum system brings to bear, whether it is in computing or whether it's in measurement, etc., which more classical systems just do not have. Now, I'll turn to the non-local description in a minute, but just to turn back to the classical world, you see, if you had a bunch of particles in classical mechanics, one could be here, shown here, the other in another room. The description is in terms of X and P for each particle, a local set of variables. They can then, of course, interact with each other. Maybe this particle jiggles around, it lets off a electromagnetic wave. If it's charged, that electromagnetic wave locally propagates, gets to the second room, interacts with the second particle if it's charged. But the entire description is local. The description of the initial particles is local. How they interact with the environment is local. No signal can be transmitted instantaneously. At best, it can go at the speed of light locally as a wave. This is very different from what happens in quantum mechanics, at least insofar as we describe systems. Okay, we are slowly beginning to understand this, and the talk will be mostly about this aspect. I'm going to describe it, give you a simple example soon, but let me say here, it was really Einstein, absolutely brilliant in this subject too, who put his finger on this weirdness, and it caused him a great deal of disquiet. He called it a kind of spooky action at a distance. You see, Einstein more than anybody understood that physics had to be local, because nothing, if there was a signal which could propagate instantaneously, the entire edifice of relativity would instantaneously crumble. Nothing can propagate faster than the speed of light. So Einstein understood better than anybody else that physics had to be local. And yet there was this non-locality in our description of systems in quantum mechanics. And Einstein said, how can that be? It must mean only one of two things. If all physics is local, but we are not able to describe it locally, then perhaps we have not found the ultimate description of reality, because that should be local, reflecting the inherent locality of physics. Or perhaps hidden in quantum mechanics is a kind of non-locality, which is preventing us from finding such a local description. This was Einstein's point. And he really worried a lot about it. As you know, he had a lot of problems with quantum mechanics. And this particular worry or aspect of his concern was stated beautifully in the EPR paradox, as it's called, due to Einstein, Podolsky, and Rosen. Okay, let's turn to an example. Let's take two electrons, two spin half systems. Now, most of you have done a course in quantum mechanics. You might know what spin half is, but if you don't, that's fine. Think of them as two magnets. They can either be up or down. And in the quantum world, if you have two of these spin half particles, then you can have them in a state where the total spin is zero, the total the orientation, net orientation of both together, if you like, is zero, has no orientation, but it's of this type. The state is of this type. The first electron is up, the second is down, minus, this is the wave function, so phases are important, minus the first is down and the second is up. Okay, this is the wave function. And we can have these two electrons far separated, so they're not very close together. Just to dramatize, one of them could be on Earth, the second could be in Andromeda. That's hard to set up experimentally, but just to make the point, they can be far apart, but in a spin zero state. In that case, the description of the system, the wave function which describes it, would have to be a non-local one. I would not be able to describe each electron by itself. I would have to describe the two together by saying that the system is in the state such that if one is up, the other is down. If the other is down, the second is up. It has to be done together. It's this non-locality in our description that worried Einstein, okay? And today we would say that this two electron system, this two spin half system is entangled. There's clearly a correlation between them. We don't know whether any one of them is up or down, but we know if one is up, the other is down. And that's the entanglement. That's the correlation between them. Okay, if we measure the spin of the first electron along some axis, say the z-axis, the orientation of that magnet along the z-axis, we may get either up or down, either. We don't know which, we'll get one with equal probability in that particular case actually. But what we do know, interestingly, is if the first one comes out up plus, then the other one will come out in the, we'll know immediately actually. Let me say that again, what we don't know whether the first electron is up or down, but what we can say with total confidence, given our knowledge of quantum mechanics, is if we measure the first electron and it turns up, then the second one will be down. And if the first one is down after the measurement, the first one, did I say that wrong? If the first one is down, the second one will be up. Okay, so this is known, and this is because the state is entangled. Okay, now you might say, well, why is this causing so much concern. It's not as if we don't know classical systems which are correlated. All you're describing is a kind of correlation. For example, okay, I usually wear socks of the same color, not always, but usually. So if you saw one, say my left sock and found it was red, well, then you can say that my right sock is also red. Okay, well, that's a kind of correlation. There's nothing funny about that. Why am I so excited about the correlation I described in this 2-electron system? There is, I believe, an intrinsic difference for the 2 electrons. And it stems from the fact that the first electron does not have its definite spin, and actually in any direction. I could have measured the spin of the first electron, I said in the Z direction when I spoke earlier, but equally well in the X, in the Y directions. And for all those measurements, I would not get a definite answer. It could either be up or down along any of those directions. But despite that ignorance, despite it not having a definite spin, we would always find that the second electron is perfectly anti-correlated. If the first one turned up to be up or down along any direction, the second would be oppositely oriented. This is the new feature in quantum mechanics. We don't have knowledge, perfect knowledge about any subpart of a system, yet they can be entangled so that there are these kind of perfect correlations between them. And because of that, our description of the system necessarily has to be non-local. Okay, now Einstein's objection remained a kind of philosophical one. Oh, he was complaining about our description of the system. Nobody argued about the consequences of experiment. Physics went on. Many decades passed till the 1960s when John Bell, in brilliant work, absolutely brilliant work, put his finger on Einstein's objection and showed that one could do experiments to actually try and decide whether quantum mechanics was correct or whether there was a more complete description, as Einstein would have liked, which was inherently local. Okay, so as I said to you, Einstein's point was, well, if all physics is local, there should be a more complete description, perhaps with additional hidden variables which we are missing and not putting into quantum mechanics. And if we put them in that more complete description, our description of a state also should be local. Like in classical mechanics, each particle has a position, momentum locally defined. So too in this more complete description of reality in quantum mechanics. This is what Einstein wanted. What Bell pointed out was that actually you could tell experimentally whether nature behaved like quantum mechanics told it to, with these kind of non-local correlations due to entanglement, or whether it behaved more like Einstein wanted in terms of a local theory, although perhaps with more extra hidden variables. Okay, and this was really Bell's brilliant contribution. Again, happened in 60s, many decades went by, another, I would say, 50 years before the true significance of his work is beginning to dawn on us, now resulting in this new frontier, as I said, of science. Okay, and so what was Bell's crucial insight? I want to take 2 minutes to describe this to you, and then we'll go on. What he found was that there was a way, experimentally, when you set up a clever enough experiment, to have consequences where if you had a classical system with arbitrarily more hidden variables we may not have found yet, okay, arbitrarily more hidden variables, some of which we may not even fully know what they are, doesn't matter. As long as it's a classical system of the usual kind, and I'll make that more precise, then there would be some inequalities which the experiments would have to meet. And in the quantum world, those inequalities would have to be violated if the underlying description was an entangled state. And then, therefore, this becomes now an experimental question, not a philosophical question. You can do an experiment and decide, is quantum mechanics right? Or is there possibly a more, as Einstein would like to call it, complete theory description with hidden variables. Okay, so he turned it into a crystal clear experimental question. The only thing one needs to assume about the classical system is that probabilities which might arise because there are extra variables we don't know about, and their ignorance is resulting in probabilities, that those probabilities have to be positive, right? That is always the case. It's almost a definition of probabilities. If you flip a coin in the classical world, the chance that it comes up heads or tails is probabilistic because the trajectory of the coin is so complicated. It interacts with all kinds of air molecules. You toss it in a particular way and so on. But the probabilistic description, because of your ignorance of those variables you're not keeping track of, always results in probabilities which are added and which are positive, okay, to give you net probabilities. So what he showed was just using the fact that probabilities are positive, you would have to have some inequalities that a classical theory would have to preserve and the quantum world would violate. That's it. So little went in and such a profound result came out. Okay, it's really the hallmark of theory at the highest levels. I should say one more thing, you know, the mathematics going into Bell's work is trivial. It's literally 2 lines. I think, again, that's always the hallmark of great physics, usually. It's not the mathematics, it's the physics insights, which are so difficult sometimes to come to, because putting words together with mathematics and experiment, which is at the heart of theoretical physics, is so hard to do, especially when the words pertain to experiences which are counterintuitive. Okay, now I'm going to skip the details just to give you an idea. You can take one of those entangled spin-half systems. You have to measure the spin in 3 possible directions, which are not back-to-back. So 3 directions, A, B, and C. A can be along the y-axis, B can be along the x-axis, C can be at 90 degrees. And then you have this kind of a Bell's inequality, which a local hidden variable theory would have to preserve, and quantum mechanics you can show for this orientation of the 3 axis violates this inequality for the spin 0 entangled state. Here is a beautiful experiment done by Alain Aspect and his collaborators already some decades ago. This S of theta is one of these probabilities. It's a slightly more complicated experiment than for the spin-half system I described. The hatched region is the one which is classically forbidden, not allowed by just the fact that probabilities would have to be positive. So that's the disallowed region. Quantum mechanically, the theory predicts a curve which is drawn here, and the experimental dots are shown here in black. I hope you can see them. The quantum mechanical theory goes clearly through the classical forbidden region, and the experimental dots clearly lie very well on that curve, okay, without any doubt, even given the error bars. And it's this kind of experiment done now by many people, after Alain Aspect also, which have confirmed that quantum mechanics is correct, if, and particularly if we are dealing with these kinds of entangled systems, which have in their description this kind of non-locality, then the quantum world behaves differently from the classical. Yes, go ahead, please.
Sandip, this is Jyotishman. Sandip, could you elaborate on the exact nature of the experiment? What was done here?
In the BCHSH experiment?
Yes, yes.
Okay, I'll have to go back and look, Jyotishman. I don't remember. It's more complicated than just taking the spin-half system and measuring 3 axes. You have to set up the system a little more carefully, and the variables also are not quite these probabilities. So let me not try to do it online in real time.
But it is actually picking up spins of
yes.
electrons or
photons.
Some other particles. Okay.
Photons, actually photons. Okay. That's right. Spins of photons. You can have photons which are in a similarly entangled state, and then you measure the spins of these photons suitably, and the polarizations, excuse me.
So essentially the polarization, yeah,
yes.
Not the spin as such, but
that's right, that's right. You measure the polarizations, but the setup is a little bit more complicated, and I should have had a picture for you. I don't, so I'll sort of get it wrong if I try to describe it, but it's conceptually not very different. You have photons which are polarized, and entangled, and then you carry out measurements of their polarizations, changing the axis along which you measure the polarizations.
Okay.
And then you get this kind of result. Yeah.
So those experiments have been done quite a bit with with photon polarized states, polarized photons in a cavity or other kinds of ways of looking at single photon entanglements, even with a cavity, for example. So those experiments have been done, but I just wanted to know the nature of these classes of experiments.
Okay.
So this was in 60s, is it?
Alain Aspec's are in, short, I would say certainly by the 70s, he had very conclusive experiments. I might have the date wrong, but yes, certainly I think. But by now been repeated by many other groups. In fact, up to some of the more recent ones have results which up to 9 standard deviations actually tell apart quantum mechanics from the local hidden variable theories. These get more elaborate, but this is already from Alain Aspec's original work, which is only a slightly souped up version of the kind of setup I was describing. Yeah. Okay. So I'll come back to you, Jyotishman, with more details. I want to describe, before we go on, a slightly humorous anecdote here, because it also illustrates some of the strengths of the French system, which I think we share in some ways in India and particularly in TIFR. When Bell wrote his famous paper, it, as I was saying, didn't attract too much attention, but Aspect was a young man. He got very excited. He decided to do these experiments, and well, he was in France, and Bell was a physicist at CERN in Geneva, so it's not too far. He took the train up and went on and on telling Bell how he was going to do the experiments. And as he has narrated, Aspect in his memoirs, recollections, Bell was quiet for the entire, while that Aspect was speaking. And after that, when Aspect stopped, Bell asked one question first. He said, so Aspect recalls, eventually I stopped talking and the first question came from Bell. Have you got a permanent position? And, Aspect said, yes, I do. And then Bell said, by all means, go ahead and test this, because it's a great experiment to do. But if you didn't have the position, I would say, don't do it, because nobody in the world is paying attention. Okay, and the reason why Aspect could do this experiment, it took him some years, is because the French system is a little bit like the Indian system in that they give tenured positions to young people early on. And that gives you the kind of, freedom to go out on a limb and do something really great, which Aspect did. So I think it's worth keeping that in mind for our own organization also. Okay, anyway, the experiment have been beautifully carried out. And as I say, quantum mechanics stands vindicated. Okay, so now in the rest of the talk, let's try to understand entanglement a little bit. This kind of two-state system, the spin-half system that I've been using so far, I'll call a qubit. And the kind of entangled spin-zero state that I was referring to in honor of Bell, we'll call, as is often done now, a Bell pair as we go along. So just so we set the terminology. Okay, now in fact, more as time has progressed, people have realized that this essential weirdness of entanglement is a kind of resource which can be put to use, and much of the current excitement comes from trying to find new and interesting uses for entanglement, which we'll try to describe, and also an understanding of known phenomena in physics or partially known phenomena with a view towards quantum information and the kind of properties of quantum systems is proving, as I said, rewarding in many areas like condensed matter physics, even quantum gravity, and so on. And I hope to give you some kind of a bird's eye view of that. Before I go on, let me acknowledge the word entanglement frontier was coined by John Preskill some time ago in the 25th Solvay conference. These Solvay conferences are famous where people get together and discuss some important things. There were Solvay conferences at the birth of quantum mechanics and so on. And in a Solvay conference, I should have had the date here, now almost a decade ago, Preskill coined this phrase. John was my thesis supervisor, so I have to give him due credit, pay homage. And he said there, already about a decade ago, quantum information science explores the frontiers of highly complex quantum states, the entanglement frontier. We hope to hasten the day when well-controlled quantum systems can perform tasks surpassing what can be done in the classical world. One way to achieve such quantum supremacy, this is another word he coined, which has also gained some currency, would be to run an algorithm on a quantum computer which solves a problem with a super polynomial speedup relative to classical computers. But there may be other ways, such as simulating exotic quantum states of strongly correlated matter. So what I want to do is just give you a little bit of bird's eye view of how this could impact computing. This is not an area in which I'm an expert by any means. Others here in TIFR are much bigger experts. I hope Vijay is here. I asked Vijay Raghavan to come to answer all the tough questions, but at any rate,
I'm here.
Okay, good. And I hope Jay Kumar is here. I'm not sure. Jay Kumar certainly knows a lot, and Pranab Sen on the algorithms end. So we have many experts, but I have to tell you a little bit because it's so exciting about what potential these kind of computers might have. So what's the basic idea? And the idea actually, again, is an old one. In fact, goes back to Richard Feynman, who very presciently realized that one might be able to build such computers using quantum mechanics, which are much more powerful. And the basic idea, one aspect of the underlying ideas here is that the description of states in quantum mechanics is in terms of a Hilbert space, which I'll describe to you in a minute. And the Hilbert space has a lot of states, an exponentially large number of states. And as Feynman said, Hilbert space is a big place. And please allow me for a minute to say, I had the great fortune of beginning my graduate career working with Richard Feynman, and he would take us out for dinner sometimes after our discussions and would tell us about quantum computers. And it just fell on, I feel so stupid because it just fell on my deaf ears, hearing it from the big man. I remember him saying, Hilbert space is a big place, fell on my deaf ears because I didn't understand the significance of it. But this is one aspect of it. Okay, what do I mean by saying Hilbert space is a big place? If you take a spin-half system, it can be either up or down, so it can be in two states. If you take n of them, each of them, if you take n spin-halves, each of them can be up or down. Two possibilities for each of them. Total number of states can be 2 to the n. So that's the dimension of the full space called the Hilbert space. That's another name for the full set of states, if you like, which grows exponentially in the number of qubits. Now, if I just told that to you, you'd say, what's the big deal? If I had bits instead of qubits, each bit can be yes or no. Again, if I have n of these bits, the number of possibilities will be 2 to the n. So what's the big deal? Why are qubits so different from bits? And the answer is that not only can you store, therefore, to begin with, if you had 100 qubits, since you can have 2 to the 100 states, a lot of information in 100 qubits, exponentially large amount of information, but, and this is where the power of quantum mechanics comes in, you can have a state with an amplitude to be in all of these states, some amplitude to be in any one of these states, and simultaneously evolve it. It's this fact that the wave function evolves simultaneously in Hilbert space that gives you really some of the power behind the idea of quantum computing. It's not as if you have to build each configuration out of bits, each of the 200 configurations out of bits, evolve them through the computer and find the endpoint and then see what is the outcome for all the possible states. You build one state of the set of qubits with an amplitude to be in any one of these 2 to the 100 possible states, allow the system to evolve in one shot, and with luck, get an answer you want. Not always easy to extract that answer because of the inherently probabilistic aspects of quantum mechanics, but if you're clever for some algorithms, extract an answer that you want. So it's really the fact that Hilbert space is a big place, along with Feynman's sum over histories. As some of you know, Feynman reformulated in brilliant work, which he did for his PhD thesis, for the graduate students here, it's worth remembering, this is his PhD thesis, he reformulated quantum mechanics as a sum over various paths. His idea was you can think of quantum mechanics as summing over all possible paths as a system evolves, each path going through all, sampling the various states of the Hilbert space the system can be in. So a quantum system in its evolution has a kind of inherent parallelism. And it's this quantum parallelism combined with the large dimensionality of the space which is being sampled that gives rise to some of the power of a quantum computer. Okay, that's the basic idea, the fact that you sample over all these paths. But of course, there's much more to it. You have to come up with a clever algorithm so that at the end of the day, you can extract useful information. This algorithm, one early example of that was the prime number factorization algorithm by Peter Shor. I won't have the time to go into it. I'll just give you the basic idea. It's really very beautiful, very simple to understand again. If you're given a big number and you asked what are its prime factors, like 21's factors are 7 into 3. If I give you a bigger number after some more work, you'd be able to give it to me. If the number gets bigger and bigger, this task of finding the prime factors gets harder and harder. In a classical computer, that time is exponential order. So there's some prefactor, some number here, but it's order roughly log n. N is the size of the number to the 1/3 with some corrections. In a quantum computer, if you could build it in a quantum algorithm that Peter Shor devised, he found it was only order log n square, roughly exponentially faster. Not quite, because this is e to the log n to the 1/3, but still roughly, instead of e to something involving log n, just log n. And you know, this difference between an exponential and not having the exponential is a big difference, as you can imagine, if n is a big number, because log n then is much smaller than e to the log n, or even e to the log n to the 1/3. So this, I remember when this algorithm came out, it really set the entire world of theoretical physics and so on fire, because it really, and computer science, I think, because it illustrated the possibility of what a quantum computer could achieve. Okay, now, of course, and this is, by the way, an important algorithm because prime number factorization is at the root of encryption and so on in online transactions and so on. And of course, we all know that part of the motivation behind quantum computers is to do problems like this, although this one is very hard, but it really motivates us. I got to show Vijay's picture here. This is a slide I show everywhere else. I was preparing this talk. I said, I've got to show it in TIFR. So here is Vijay. I'll show you his picture. Vijay, here you are with your dilution fridge. And I know he's going to get another one soon. So good for you. What he's holding up, he'll tell you. I won't dare. Anyway, and well, he has a few qubit device, but it's performing well at that level with similar devices built elsewhere. So let's hope. Okay, but there's been also a lot of hype in the area. So let me say, and Vijay and others can say more, that we have a long ways to go. Error correction is very crucial. And the underlying ideas behind error correction, if they are to be workable, are very beautiful, and they're all tied to entanglement, as far as I know, every workable idea that I've studied. And the idea is very beautiful. It is to put the non-local aspect of entanglement I was emphasizing to use in the following way. Let's accept that quantum systems have non-local correlations like this. If errors arise locally, say your two spins, they are entangled. The errors in each spin arise locally, then with enough entanglement spread out non-locally, you might be able to correct for those local errors, because information in entanglement can be spread out non-locally and therefore protected against local errors. This is the key idea. It's a beautiful idea, putting entanglement to use. You put in redundancy, which is always there in error correction, along with entanglement, to try and build a system which then is protected against errors. For example, if you're at a state which is a combination of spin up and spin down with some amplitude, you make a threefold redundant state So alpha plus plus plus, you have 3 spin ups and 3 spin downs. Okay, and then if there is a flip error, so up becomes down due to some error, you can look at the other 2 spins and decide by majority rule what the spin should have been. As long as there is a small error rate and only one of the spins is going to flip, because the errors are local, you can always use the majority rule to correct at least for the spin flip error. Of course, there are other kinds of errors. There are phase errors, there's decoherence, you got to work harder. But this is the basic idea, which makes one hopeful that perhaps we can conquer errors and build a workable computer. Okay, so many challenges remain. Others will tell you more about them, but it's a very promising direction. And if we can't do the prime number problem, hopefully we can do other problems, which will still be very interesting, do computations or calculations in chemistry, which will still be very interesting in terms of teaching us about the real world and putting quantum mechanics to use for computing. I'm going to shift gears and become more theoretical now, try to tell you a little bit about how the progress in quantum information and so on is beginning to impact other branches of science. So this is the flow of knowledge now going the other way, which is how I got sort of interested in the whole subject. I'm going to take a step back as a theorist and ask the question, okay, quantum systems have this interesting property called entanglement. How can we precisely quantify it? I shouldn't say measure, but how can we precisely quantify it? The idea is very simple. Let's say we have a general system with 2 parts, A and B. They share some entanglement. We want to figure out how much entanglement there is. Say because we are convinced that entanglement is a resource which can be put to use in error correction or whatever, and we want to know how much of that resource do we have in the system with 2 parts. Now there's a mathematical way to give the answer, construct the density matrix of one or the other, take its von Neumann entropy, blah, blah, blah. I won't give you that mathematical answer, but I'll give you an operational answer, because in the end, operational answers are the physical ones in physics. And the operational answer is quite beautiful. Think of the following. It's called an entanglement distillation operation in quantum information theory. Let's use as our unit of entanglement bell pairs. You know, this kind of spin zero state we were discussing made out of 2 spin halves. Or instead of spin half, we can just say 1 qubit. You have 2 qubits entangled in a zero state, okay, in a zero spin state. And we call that 1 bell pair, and that's our currency for entanglement. And to ask how much entanglement there is between a system, between 2 parts of a system, let's ask, can we do operations either on one part or on the other, not on both together, but only on one or the other? And after that, ask how many maximum bell pairs can we generate in this way? That maximum number of bell pairs becomes a measure of the entanglement shared between A and B, okay? That's the basic idea. Use bell pairs as currency, start with totally unentangled qubits. On the left and right, some number. The left interact with A, the right interact with B, and at the end of the day, ask how many maximum entangled bell pairs can you create in this way? That maximum number is the entanglement between A and B. Now, if you have typical systems made out of spins and so on, all the entanglement between A and B can be removed through such local operations, etc., and transferred to initially unentangled qubits. And this then can be our definition of entanglement. But it turns out that the actual world is more interesting and subtle. And this has to do with the fact that precisely because of quantum mechanics, you can't always separate systems very clearly. Not just our description of the system, but also other properties of the system. And I'm going to explain this idea to you, because on the one hand, we want to ask how much entanglement they share. On the other hand, we don't have a very clear way, because of quantum mechanics, as I'll explain, to even separate them. So therefore, how much entanglement you can extract out of them becomes an interesting theoretical question, which has interesting ramifications, as I'll try to explain. Okay, what do I mean by saying you can't always separate degrees of freedom locally? into a quantum system. See, in the two spin halves, they were entangled, but I could separate the degrees of freedom. I could say I have a spin half here and a spin half there, and then they are entangled. But you can't always even say that much about physical systems. Why is that the case? This is even true in electromagnetism. So let me try to explain that for you. In classical electromagnetism, we describe the system in terms of electric and magnetic fields. Sometimes we use gauge potentials. For example, B is curl of A, E is made out of A, the vector potential A and A0. Some of you know this when you do electromagnetism, but the vector potential is not essential. The underlying description is really in terms of E and B, and if you have charged particles, they respond to the electric and magnetic fields. But the quantum world is different. And this is exemplified by a very beautiful effect in the quantum world called the Aharonov-Bohm effect. Some of you know about it, but I'm going to just explain it to you briefly. Suppose you had a bar magnet which was going through the center of a cylinder. It's a hollow cavity, and the bar magnet goes through it. And you had a two-dimensional system of electrons living entirely on the surface of the cylinder, okay, which I've tried to denote here. The electrons can't go in, they just live on the surface of the cylinder. You can have such two-dimensional materials that you can prepare and so on. This is the idealization of that. So you have a two-dimensional system. It's on the surface, threaded by a magnetic field. The system can't penetrate and sense the magnetic field itself, but it can only be on the surface. Well, if it were classical, since there's no magnetic field on the surface, the system would not see any magnetic field. But in the quantum world, even though the system is on the surface where the magnetic field identically vanishes, it sees the influence of the magnetic field. And it sees it because in the quantum world, systems respond to the gauge potential, not the magnetic field. Not quite the gauge potential, not all aspects of the gauge potential, but some aspects of them. In this case, only the integral of the gauge potential along a circle which is threaded by the magnetic field. That integral measures the total flux of the magnetic field going through the circle. Some of you might remember this from electromagnetism. That's the whole way it works out. B dot ds is A dot dl, and A dot dl therefore is the total magnetic flux. And it turns out that even though B may vanish, if A dot dl's integral is non-zero, the system is going to respond to that. And this is something which is experimentally checked. Again, when it was first realized about quantum mechanics, it caused a lot of amazement. But now we know it's true that the Aharonov-Bohm effect is there to stay. It is again another essential aspect of quantum mechanics. And what that tells us is that locally, you can change the value of A. It doesn't matter on the surface of the cylinder. But what you can't change is the global integral of A. That has experimental repercussions. There's no significance to the local value of A, even in quantum mechanics, but the global value of A, the integral, that has an experimental significance. So now the question is this: in a context like this, if I had to take some part of the surface of the cylinder, I have a two-dimensional material made out of two parts, and say, how entangled is one part with the rest? How am I going to do that if even the underlying degrees of freedom are not localizable? Okay, this is the kind of question. I don't have localized spins, and then I ask how entangled they are. Even the degrees of freedom are not localizable. And even if I then asked how entangled are they, what is the meaning operationally of the answer I get? Okay, this is the kind of question which we try to answer in our work with some very bright students, Ronak Soni, Shudip Ghosh, Upamanyu, who's here in, I think, this call. Ronak is graduated, Shudip is graduated by now from ICTS, Shudip. And we try to give a precise definition in the kind of theory that electromagnetism is. More generally, such theories go by the name of gauge theories, and such theories underlie our understanding not only of electromagnetism, but the other fundamental forces of nature as well, the strong force, the weak force, and in a sense also gravity, which is a gauge theory, although as always gravity is more complicated when you think about entanglement there as well. Okay, and what we found was that you could give a sensible definition of entanglement in such theories, and I'm going to explain to you operationally what was the result of our investigation. We again start with two parts to a system. Now in a gauge theory, they share some entanglement, which we are trying to make precise, okay? And we try to do it by first taking n qubits, 2n qubits, which are totally unentangled, and transferring the entanglement from A to the left qubits and B to the right qubits. Well, what we find is you can't transfer all the entanglement out, because some of that entanglement is in non-local degrees of freedom in the system, but there is a maximum amount of entanglement you can take out, which you can make precise. So there is a maximum number of Bell pairs you can produce, and some irreducible amount of entanglement you cannot remove. Both can be made precise. Both were made precise in our work, never mind what the details are. Just to say the amount you can distill or remove tells you how much resource you can extract from such systems, and the amount you can't is a measure of the kind of topology of configurations in the system. Just as the gauge potential having an experimental significance was ultimately because you were on the surface of the cylinder and there was a circle you couldn't contract because you couldn't go into the core, that non-trivial topological aspect of the gauge potential was responsible for this Bohm-Aronoff effect. More generally, also, there are aspects in the non-distillability of entanglement, which tells you about the topology of gauge fields and the particular kind of state you are in. Okay, so it tells you something, even the non-distillable part. And that in turn allows you to understand various kinds of states of matter. How much non-distillable or topological impediment do they have to the extraction of entanglement? Sounds a little theoretical, but it has practical consequences, which I want to turn to now by telling you about connections with condensed matter physics, and then we'll end the talk. You know, one of the most important questions I would say in standard condensed matter physics, again, others can correct me, is how do you classify phases of matter? You know, someone gives you a phase of matter, you want to know, is it a solid? Is it a liquid? Is it a gas? If it's magnetic, is it magnetized, etc. And Landau, in brilliant work many decades ago, told us that you should think of symmetries. Symmetries allow you to classify phases. A solid breaks translational invariance, a gas phase does not break translational invariance. For spins, a ferromagnetic phase breaks the rotational invariance of spins, and a non-ferromagnetic phase may not break it, etc. Think in terms of symmetries. Symmetries allow for classification of phases. But we have increasingly found phases of matter where that is not true. How then do you classify such phases? I'm almost at the end, Jyotishman, just 2 minutes more. And it turns out—
no issues. Basically, you can, I typically let speakers go up to 5:50.
Okay, I'll be done before that. It turns out for some of these new exotic phases that we are finding experimentally, interestingly, entanglement turns out to be a good way to try and classify them. You can't tell them apart from symmetries like Landau told us, but if you can find how entangled are their ground states, then you can tell these phases apart, theoretically, okay? The fractional quantum Hall effect is such a phase of matter. It has a very interesting structure in the entanglement of its ground state wave function, okay, with long range entanglement. It's a much more complicated phase, actually, conceptually speaking, compared to the integer Hall effect. And entanglement is actually, as I said, a useful way to distinguish the two. Here is the integer Hall effect. You might have seen it. The Hall effect measures the transverse conductivity. You take a system, you send a current through it. It's two-dimensional. There's a magnetic field threading it, and you measure the transverse voltage that is set up. And from there, a transverse conductance or resistance. And it shows for some materials this kind of step-like structure at integer values in suitable units. That's the integer effect. Similarly, you can get fractional values. That's the fractional quantum Hall effect. It's very 2 Nobel Prizes and more, I think, have gone for these discoveries, which are very interesting. And you must have heard about them. It turns out, from a theoretical point of view, the underlying description of the fractional quantum Hall effect, a very good description is provided by a gauge theory. A gauge theory conceptually sort of the type that electromagnetism is. quite different in its actual structure. It's called Chern-Simons gauge theory, never mind, but it's a theory of that type with similar non-local effects. And again, if you can make entanglement precise, which as I was telling you, we can, then in fact, you can use entanglement cleverly to tell the different plateaus of the fractional Hall effect or the different phases of the Hall effect apart from each other. And also from the structure of the entanglement, learn about the topology underlying these gauge fields in each of those states. So that's a very interesting connection. This calculation of topological entanglement entropy was done anyway, even before our work, by Kitaev and Preskill and Levin and Webb. But it cast in the light of general understanding of gauge theories, it tells you about the distillable and non-distillable aspects as well. Okay, so just to tell you that as our understanding of entanglement grows, it's informing also our understanding of interesting new phases with topologically non-trivial aspects in condensed matter physics. And that's an example. Another example is provided by gravity, where the deepest mysteries of black holes, it turns out, also get connected to entanglement entropy. I'm going to skip that totally, although it's such a beautiful set of developments in its own right with much recent activity, because I'm running out of time, I think. Well, maybe I'll be tempted to just give you a bit of a teaser here. You know, Hawking had a very seminal result many decades ago, where he showed that black holes are not really black. This is because they give out radiation. And in fact, the radiation is of a black body type, characterized by a single number, like black body radiation is, which is the temperature of the black hole in this case. Well, it turns out from the modern perspective, the way to understand black hole evaporation is through entanglement. In fact, that provides the really deep understanding of what's going on. You should think of black hole evaporation as follows. A pair is produced due to quantum fluctuations. This can be a pair of electron and positron, or even just two photons in entangled states. A pair is produced near the surface of a black hole. One partner of the pair flies off to infinity and turns up as radiation. The other partner falls into the black hole and goes off into the singularity, never to return. Thus, the entanglement between the pair is lost to the outside world. Only one partner survives. It's this lost entanglement that results in the radiation having a thermal character. And in fact, many years ago, in '94, when I was a postdoc with Fiola, Preskill, and Strominger, Hawking already had his result, but we redid the result in light of entanglement and showed in a simple two-dimensional model that entanglement, in fact, was a very precise way to think about Hawking evaporation and led to the result that the radiation was thermal because of a loss of entanglement. Connecting the two. This is very early on in the days when entanglement was just being understood, especially in the context of gravity and so on. More recently, just last year, very interesting work returning to such 2D models, showing that in fact subtle effects which we had ignored, others had ignored, Hawking had ignored, in fact might result in the final answer from black hole evaporation being quite different. And instead of a purely thermal state coming out, a state which in the end is not thermal, and in which the information which goes into producing the black hole is not lost. So this is a kind of, I'm just rushing through this, I apologize, but I want to give you just a flavor for how entanglement is beginning to inform our study of not just condensed matter physics and so on, but also quantum gravity. Okay, so to summarize, you're slowly coming to grips with the strangeness of quantum mechanics. Quantum systems can be correlated in this very distinctive manner called entanglement, which allows them to violate Bell's inequalities and behave in ways very different from classical states or systems. And increasingly, as we understand entanglement, it's proving to be a resource with which we hope to build quantum computers free from errors, a resource, and I just didn't talk about this, but these are vast areas about which I know little, but with great potential, I think, ways to do new kinds of sensing and metrology, measurements, also new kinds of communication, secure from eavesdropping and so on. Also, and I touched on this, entanglement is proving to be a resource in terms of shedding light on other branches of physics. And we hope these developments will continue in the future. And I invite you all to join in the fun, which I think really awaits us. I think it's going to be a gorgeous period for all of physics going forward. This brings me to the end of my colloquium, but I'm going to now have a postscript. Please forgive me for 2 minutes, not strictly science, but I think important. Please excuse me if you think it's inappropriate. And I want to draw light to the following fact for us all in TIFR. Some of you know, I'm sure, in the 2000 budget, the Honorable Finance Minister made a huge announcement. She announced a rupees 8,000 crore national mission for quantum technologies and applications. 8,000 crore mission, okay? This is huge. And this shows the importance seen in the highest circles, not only in science, but government for this area, correctly, I feel. Now, I'm very proud to say that TIFR played an important role in the discussions leading up to this announcement. As you can imagine, there was a lot of backroom work, and TIFR played a key role. He got 3 photos here, Jay Kumar, a youthful Jay Kumar, the younger Vijay Raghavan, if I can call you that, and the senior Vijay Raghavan. Especially, I put our Vijay Raghavan in the center because he's played an absolutely crucial role, not only in the events leading up to that, but in the subsequent work to prepare the DPR, which is a mammoth thing, which is going on, and I hope will soon be now unveiled, the final the detailed project report, after which hopefully funds can start flowing. So this is a very, very important juncture in this field, I feel, going forward in India. Other institutions are really getting their acts, if I can say, together, getting organized. For example, IISc now has a group of about 40 faculty, Quantum Technologies Initiative, and so on. And I really feel we need to also get going, not be caught unprepared. We played a key role, but we need to now position ourselves properly. It's exactly the kind of role we should be playing on the national and international scene. And I really invite you all, some of you, of course, are, as I said, very actively at the forefronts, but I invite you all to also think about it and see if you would like to get involved, because I think there's a lot of scope for great science to be done. I should also point out here, there are already some important initiatives ongoing where TIFR is involved. There's the DYSL lab with DRDO and IIT Bombay. There's collaboration with BRC, there's collaboration with TCS and so on. But I think we can build on all this and do much more. So thank you very, very much for your time. I'm going to show you one final slide, you know, the gorgeous banyan tree we are so proud of, but what holds it up? If you look carefully, it's the hugely entangled roots. And maybe that's how reality is, ultimately held up by quantum entanglement. Thank you.
Okay, so Sandip, thank you for this very elaborate talk on entanglement. And I think the chat box was buzzing with questions. I did not stop you.
I'm sorry.
Because the questions need a separate time and discussion. So I'm going to first take a few questions from students. So one student, Dibbashankar. Dibbashankar, can you actually unmute yourself?
Yeah, hi. So it was not a question rather than a reply that in the chat, it was being talked about how entanglement violates STR. And so I disagreed that entanglement doesn't violate STR because no useful information is conveyed through entanglement.
What is STR? Sorry.
Special theory of relativity.
Oh, right. Okay, go ahead. Yes.
So yeah, my point was that, I mean, I do not understand how entanglement violates STR because the information that is conveyed is not something that can practically be used to communicate any useful information. So like STR gives bound on that, not.
That's right. You know, as I emphasized, Einstein, for example, understood very well that you could not have a signal go faster than the speed of light. And entanglement doesn't allow you to send a signal faster than the speed of light. Now you may say, how is that? I just told you if you had this state where one electron is up, the other is down, etc. If I measure the first electron, I'll know instantly, won't I, that the second electron is in the down state. If I measure this one, it turns out to be up, I know the second one is down. Didn't I send information instantaneously? No. And this is where the probabilistic aspect of quantum mechanics comes in. You see, suppose you are sitting very far away in Andromeda, I'm carrying out the experiment on my electron on Earth, then what you know before the experiment was done is that there is a probability half that your electron is up and a probability half that your electron is down. It's true, if I knew the full state of the system, that I know if yours is up, mine is down and vice versa. But what you knew is that there's a probability of half that your electron is up or down. Now I carry out a measurement. Now, first of all, to talk about probabilities, I would need an ensemble. So let's say we had an ensemble of such pairs. Now I carry out a measurement. At the end of the day, half the time I find up and half the time I find down. And I therefore know in Andromeda after that, that half of the time you were down and half of the time you were up. But you knew that anyway before.
Yes, yes.
You knew that anyway before the experiment. So information didn't get transferred.
Yes, exactly.
This is why for a long time people thought all Einstein is raising is a philosophical objection. You know, his point was about a description of reality. Who cares? All experiments are local. But Bell showed that there are experimental consequences. And that's what changed the game, you know? So,
okay. Yeah, very interesting discussion. Okay. I would like actually, so there is a question by Sukant and then TP. I would like to take Sukant's question first and then TP. I know TP, you have raised your hand. I will take your questions. I just wanted the short ones be taken right now. Sukant, could you unmute yourself?
Yeah.
Yeah, please ask your question.
Well, my point was simply that non-locality is inbuilt into quantum mechanics because that's how you define the wave functions. It's all about waves. Waves are non-local. So why is non-locality such a strange thing? Why is such brouhaha about non-locality?
Yeah, the non-locality in quantum mechanics is a little more strange than for a classical wave, because there, you know, it's true that a wave propagates, but for example, for a water wave, you have an amplitude which is locally defined. And then of course the wave propagates with some speed as it goes along, right? And here, as I was trying to say, it's a little more, it's different because, you know, if you have two parts which are entangled, you have to simultaneously refer to both of them if you want a full description. Of course, if you're only dealing with one part, you might just use the density matrix for that part, which is a local description, but that wouldn't provide a description for the full system. So, so that's the difference, the inherent non-locality in the full description. Not so much the fact that effects, cause and effect are connected by propagation as for a water wave. But the fact that the amplitude behaves like a wave, that part is similar. It's true.
Okay. I now request Tejinder to ask his questions.
Thank you, Sandip, for your very nice talk. So, you know, as you know that quantum mechanics predicts that macroscopic systems should also exhibit entanglement, and these are not observed in nature. That is the sense of Schrodinger's cat paradox. And often the answer is given that it is because of quantum decoherence, but such an answer would also require that the many worlds interpretation of quantum mechanics be correct. So I'm curious, what are your thoughts on the cat paradox? And do you really believe in the many worlds interpretation? And if you do, how do you explain the Vaughan probability rule? Okay, that's all. Thank you. Thank you.
Okay, now, first of all, I have to say that I haven't thought deeply enough about the many worlds interpretation. That's a failure. And I should think more deeply about it. So I can't say I'm fully qualified to answer the second part of your question. But I hope to come back to you with that, and maybe we can have some more discussions. I have some initial thoughts, but I don't think I should venture them before I more carefully think them through. It is an important question, of course. What is the full, complete description of measurements and so on in quantum mechanics? So I think you're right in raising that, but let me not try to venture a answer to that. To the Schrodinger cat, I think you're right. It's very hard to keep macroscopic systems in superpositions, in quantum superpositions, due to decoherence. But in a sense, if we are going to succeed in building systems with, at least more than 1 or 2 qubits, we'll have to start doing that, right? And so one of the challenges we face in building something like a quantum computer is related to the fact that we want to keep a cat-like object with many qubits in a linear superposition and allow them to interfere as time goes by. And the hope is that with error correction and so on, we will be able to correct for decoherence. And people have made estimates, and you pay a price through redundancy, but the price is polynomial in the number of qubits. Like I was showing for correcting bit flip errors, you had to triplicate your qubits, so it was polynomial in the number of qubits, not exponential. That's the hope. I think we are at very early stages. Maybe Vijay can say more about how far we have gone experimentally vis-a-vis showing coherence in macroscopic systems. I think it's fair to say we are at early stages, but I think hopefully we'll be able to achieve that.
To add to that, Sandip, the possibility that the reason why macroscopic systems don't show quantum superposition could also be because quantum superpositions are not infinitely long-lived. As the system becomes more and more massive, the superposition lifetime goes down and down. This, of course, requires us to modify quantum mechanics. But I just want to say that such a modification is not ruled out by experiment. It may be there or it may not be there, but it's a question which has to be answered by experiment. So whether the loss of entanglement for large systems, whether it is because of decoherence and many worlds, or whether it is because you have to modify quantum mechanics, I would say this is an open question which future experiments should set.
Okay, that could be. My answer was within quantum mechanics, that there through error correction, you can hope to prevent quantum decoherence. But okay, I am not I've not studied your theory, for example, or others, but it's interesting if there is an experimental implication, especially, then that makes it interesting. And certainly it's an open question. We don't exactly understand decoherence. So I agree with that. It's an open question, and one that should be investigated more. And I think it will be. The interesting thing about where we are today is these kinds of questions, which were sort of at the left usually for philosophical thought, are becoming of technologically great importance, I think. So I think they will be addressed. So, yeah.
Okay. TP, is that all?
That's all.
Okay, thank you, TP. Thank you for the questions. I would like Krishanu and Ravi and then Vijay.
JD, sorry, I actually wanted to comment on this particular
Vijay, please,
question as well. If that's okay, otherwise I can also say it later.
Please comment now, Vijay, since it's in context.
Please.
Yeah, so I just wanted to say a few things so that we don't create too much confusion. There is a lot of different topics being discussed here. In the context of quantum computing, we are never going to be talking about objects of the size of a cat. So usually the cat is also just used as a alternate, just as a reference for something which is macroscopic, which is not a single atom or a single electron. But this idea itself, is already much more advanced, because, for example, the kind of systems I work in, the superconducting circuits, even though they have, the 2 quantized levels which we use to encode as a qubit, the object itself is millions of atoms inside. It's actually visible to the naked eye. It's, about a millimeter across, and it's a film of aluminum on a piece of silicon. But under the right conditions, when you isolate the correct degrees of freedom, it shows quantum properties.
Vijay, a million.
But
so a million is not large enough. I'm talking about 10 to the power 23.
But No, that's
Million
right.
is
But
good.
that is what I'm trying to say, that when one is trying to talk about making a useful quantum computer,
Yes, yes.
we are not going to be talking
Yes,
about
absolutely.
superpositions of the size of a macroscopic cat.
I totally agree
Nowhere,
with you. My question
nowhere
was
near
not
that.
about a quantum computer. It was a physics theoretical question. Quantum computers will never be Schrodinger cats. That is too big. I agree with you totally. I agree with you.
So that part, and then the connection with the mass and gravity being brought into the picture is again a very different model. And you have been working on this. This usually doesn't again come in the context of the kind of decoherent sources we deal with
Absolutely.
in the quantum computing.
Fully
Yeah.
agreed. Fully agreed.
Yeah.
That's
Thank
all.
you, Vijay. Thank you for
I
clarifying.
mean, I'm sorry if I caused confusion. I didn't mean to imply you'll need an Avogadro number of qubits, but what I meant to say was already for a few qubits, achieving quantum coherence is a non-trivial task, Vijay, which, okay, we are making some progress in, but I think whether we'll be able to achieve it even for the required number, let's say 100 qubits with over the kind of lifetimes we want to keep them in, is already at the cutting edge, right, of technology. Isn't that true, or what?
Yes, but we are not confused by what is causing the decoherence. What I mean is that we sort of know what is going to cause the decoherence, and either you try to minimize those sources or you try to work around it by using techniques like error correction.
I agree with you, Vijay, that if quantum mechanics is modified, that has absolutely no implications in the domain that you are working in. I'm talking of Avogadro size systems.
Okay.
Yeah. Thank you. Thank you.
That'll be harder to probe, probably, experiment.
Yes, I agree. I agree. Yes.
Okay. I think Vijay's point was mainly in the context of quantum computing, where you can fight the decoherences with error correction or other kinds of
I agree.
removing sources of these decoherences. Krishanu.
Oh, hi. Thanks, Jyotishman. And thanks, Sandip. I can't say that I have understood your talk mostly. Rather, I would say that I have probably just understood a very little. So therefore, if this question is too, stupid, just hear it. So what I'm wondering is, if what you said is correct, that, the two states of a matter can be entangled together, then when we split a laser beam into two parts, will there be some such of an entanglement, and is it measurable?
It may depend on exactly what you are doing to split it. For example, you may split a laser beam in the following way, that a single photon coming out of a laser splits into two photons, due to nonlinear effects of a crystal through which it goes. In that case, if you set up the situation right, the two photons you get might be entangled with each other, or they may not. Okay. So it could be that you use a system. In fact, something like this is used sometimes to produce entangled photons, where you have a system where you produce a pair of photons out of an initial one in such a way that various conservation laws like angular momentum, etc., guarantee that this whole system is entangled. So sometimes that could happen, may not happen all the time. So it would have to depend a little bit on what your laser beam was doing when it got split, I would say. But you can use a system like that to produce entangled photon pairs.
And one can measure this entanglement. Let's say, I split a polarized photon, polarized photon into two plane polarized photon. Is it possible? First of all,
let's say at least you got two plane polarized photons which were entangled or circularly. Right. Yeah, can you measure it? This question I skirted. I skirted because measuring entanglement, as far as I know, again, maybe some others may have other views or be better informed, but as far as I know, measuring entanglement directly is not very easy. You know, what you can do, of course, is have a system happens to be in some state with some quantum numbers, like in our case, a spin zero state for 2 spins, and then know, therefore, that it is entangled. But ab initio, carrying out a measurement of entanglement is not always easy. In fact, I don't know of, I know people are trying to do it, but I can't tell you definitively that I know of experiments where it's been pulled off, maybe for a few qubits or something. So I would be a little cautious in using the word measure, but yes, where you know that what you've prepared is entangled for various reasons, because you happen to know the state of the system. Another way to do it, just to give you an example, this is how Alain Aspect did it originally, is that you have a atom which is in an excited state from which it can de-excite not in one shot, but through 2 transitions. And the 2 photons which come out, again, due to various symmetries, come out so that they are oppositely polarized, but in this entangled way. So the first photon which comes out could be left or right circularly polarized. The second one could be left or right, but if the first one is left, the second one has to be right, and vice versa. So in these cases, through the selection rules and so on, which we absolutely trust, that the final state is entangled. But if I didn't know that and you ask me measure and find it out, it's not always very easy,
Yeah.
At least that's what I would say. Yeah.
Yeah, and I think I just wanted to add to Krishanu's question. There are experiments now with single photon sources, or even with nonlinear crystals, where you can do entangled photon spectroscopy, Krishanu, where you can use the other photon to read out what the partner photon is doing, like, for example, interacting with the material medium. So you could actually use the other photon to read information about what the other photon did in the other path, after the entanglement has been generated through a nonlinear crystal. So in principle,
clarify a little bit better, Jyotishman, for me.
No, so that is the idea, that if you have sources of photons coming in on a nonlinear crystal, you can split the laser radiation into 2 parts, conserving energy. But then you also have the phase matching, which is the momentum conservation, and you could, in principle, get 2 photons out, 2 different colors. One color interacting with the material medium, the other color is glowing through a detector, and you read out information of the other photon through the photon that you're detecting. So essentially, you are doing sort of a measurement of an absorption spectrum without actually letting the photon interact with the sample. One of the photons interact with the sample.
I see.
So this is something that is being done.
I see.
So this is something also that has come up in the recent works. Anyway, so let's actually move to Alok raised question, and then Kedar. Kedar is here. So let me first get to Alok's question. Alok, can you unmute yourself, please?
Hi, Sandip.
Hi, Alok.
It's very nice talk. I mean, but I'm not an expert, but I enjoyed listening to it. But I got puzzled about something. You were talking about entanglement entropy in terms of qubits. And, qubits, are constructed from particles.
Alok, we are not able to hear you. It's breaking up.
Okay, can you read my question?
Yes,
okay.
I will read your question.
Yeah.
What Alok says is, you talked about entanglement entropy in terms of qubits. Does it matter if these qubits are derived from integer spin particles like photons or gravitons versus fractional integer particles like electrons?
No, not
the entanglement entropy of the qubits, does it matter? Yeah.
No, not really, Alok. Okay, to give a general answer, but then we can talk about it more. As long as you have a system which has 2 parts to it with independent Hilbert spaces, which could be, say, Hilbert space for a spin 1 particle, which would have, as you know, 3 states, j equals 1, 0, and -1, or for a spin 2 for gravitons with 5 states, or a spin half with spin 2 states. But you have one Hilbert space with some number of states, another one which could even have a different number of states, as long as they are clearly demarcated Hilbert spaces, and then some general state which can have correlations and entanglement. There's a very precise way to talk about the entanglement entropy in that case. And roughly speaking, there's a formal answer I can give you in terms of density matrix, but roughly speaking, you try to organize your basis so that it looks like a bunch of basis states of the left Hilbert space entangled with basis states of the right Hilbert space. And then it doesn't much matter whether that basis refers to spin 1 or spin 2. Conceptually, it's just some basis element of the left Hilbert space and some of the right, which you have set up in this correlated way to obtain the full state. Did that sort of make sense?
I have to talk to you later about it.
One of the problems...
I'm not an expert on this, and so I should understand in private conversations.
Okay, I'll be happy to do that.
Thank you.
Thank you, Alok. Thank you for joining in again. Thank you. Kedar?
Hi, I had a very quick question about this entanglement distillation language that you used in the middle of the talk. I'm not sure I fully understood that way of thinking. So just in the condensed matter context, for example, what would the entanglement distillation operational definition, how would it distinguish between, for example, a topologically ordered phase of matter and let's say something like a topological insulator that has topologically protected end states or surface states, but no topological order?
Right.
If this is too technical, I mean, we can do this offline, but.
No, it is not. Or at least let's try and then we can continue it. The state, the second kind of state, I think, which you refer to, which has the short range entanglement with, say, if you take the Haldane antiferromagnetic
something like the Haldane chain, yes.
Right. In that case, what happens is that, let me just think this through carefully, quickly. You have these dangling end states. And I think if you just constructed the density matrix for the last end spins, you would see this entanglement, right?
Yes, that's correct, yes.
Right. And I think, but we can talk about it. I think if you would be able to distill all of it out from the system, by putting it in touch with qubits. I think so.
Okay.
If I'm not wrong, we can talk about it. That's what
that's not possible with a topologically ordered state.
Yeah. Because, it's not localized anywhere. That's the problem.
That's right.
You can't, if you're going to restrict yourself to doing experiments on only one or the other half of the sample, you can't get it out,
Right. Okay. I think I understood. Thank you.
Yeah.
Okay, thank you, Kedar. Tariq has a question. Can you unmute yourself? Yeah.
Tariq Aziz, can I ask a question?
Yes, Tariq, please.
So you see, I'm just wondering, the massive systems like BB bar, 5GB state, we have observed in Bell experiment this entanglement. That is perfectly fine. But can one think of beyond two particle systems, this entanglement phenomena?
Yes.
Whatever you have discussed effectively is all two particle system.
Yeah. No, actually, it went by quickly, but the two particle system is useful, but then the concept generalizes to many particles also. And in those condensed matter cases we were discussing, you had a very large number of particles, but they were non-trivially entangled. So to come back, you can have, say, 3 particle entanglement of a type, which is quite interesting. If you took any 2 of them, the state looks completely thermal without any interesting correlations. But when you look at all 3 of them, it turns out they're very nicely entangled together. You don't see that entanglement in any two, but when you put them together, you see them. So yes, you can have a version of this in 3 or a higher number. You have to prepare the state properly. Like here, you did it for spin 0.
Right.
There, you know, you have to prepare it properly. And actually, this case I was showing very quickly for quantum error correction is such a state. You know, it's quite interesting. If you take this state plus, 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 minus, 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 it turns out if you take any two of them, it's going to look totally like some thermal state. When 3 of them are put together, it's entangled. So for alpha and beta equal. So yeah, so you can have these kind of interestingly entangled many particle states.
If that can happen, that will open up much more computationally powerful systems.
And indeed, they use much more than 2 particle entanglement. You know, when you try to, for example, correct against errors and so on. Possibly also in algorithms, although I can't say I've studied them. I've not studied algorithms where entanglement plays a crucial role. The Shor algorithm doesn't use in its heart, which is a fast quantum Fourier transform entanglement. So anyway, but yes, certainly one needs much more than 2 particle entanglement, also for computation and so on. To be
TP has a comment on Tariq's question.
Okay,
TP.
go ahead, TP.
Tariq, I just wanted to add something which might help with your question. So it's not in the context of qubits and quantum computing, but if you ask what are the largest entangled systems for which, say, the double slit experiment has been done, that's an example of quantum entanglement. Suppose you take a molecule like C60, fullerene, you know, many years ago, the Vienna group showed that interference pattern and double slit interference is observed for C60 molecules. That's already 700 AMU. So you could think of it as that many qubits. But that number has gone up very significantly now to around 25,000 AMU. You can take a molecule as large as 25,000 AMU, pass it through a diffraction grating, and observe the diffraction pattern. So clearly quantum mechanics holds there. But the interesting question is, how large a system should be that quantum mechanics will continue to hold? Suppose it's an Avogadro number, you could make a molecule as large as having 10 to the 23 AMU. Does quantum superposition and quantum entanglement hold or not? That is the question to which we do not know the answer. So maybe it is because of decoherence that the cat paradox is resolved. Or maybe it is because when we reach that larger number, an Avogadro number, quantum theory actually breaks down. So this is the question to which we do not know the answer.
Is it that quantum theory breaks down, or is it that you are able to hold the system in that state?
Yeah, so in absence of superposition in large macroscopic systems, is it a technological limitation or is it a fundamental failure of quantum mechanics? We do not know the answer to that question. It is being tested in the lab. Hopefully one day we'll know.
Yeah, okay.
Okay. I think Vijay.
Sorry, the only small caveat I would make, if you don't mind, TP, is, and you of course know this, but I'm just saying, superposition is different from entanglement. And to the extent, Tariq, your original point was about entanglement.
Yes.
Yes, it's very well taken. I did mostly focus on the 2 particle case, but it's a much more general phenomena.
Yeah, but you know, Sandip, if you take a molecule like
Fine.
a molecule like C60, then that's an entangled system. If you observe quantum superposition in C60, that's quantum entanglement because it's a bound system, you see. It's like the 700 atoms or 700 nucleons of C60 are in an entangled state of upslit and downslit. That's what I mean.
Okay. Thank you, TP. Vijay, do you have a comment on this?
Yeah, just briefly, I'm not sure if that was one of the aspects of the original question is for any practical usage of the quantum computer, we have to make much larger entangled states and much larger superposition states as well. Just a point that you can actually do that by only making pairwise interaction. So this was another important theorem which was sort of proven, that you can create larger entangled state, but only sort of by making interactions 2 at a time. So pairwise interaction is enough, though might not always be the most efficient.
Yeah. This is an important point. This is an important point. Yes.
Okay. Cool. Sandip, I'm sorry, we have to conclude the colloquium. However, there were like questions from the YouTube channel. One of them by MP Sharma is already addressed. Is quantum teleportation faster than the speed of light? If not, what is the reason? I think the very first question you addressed it with Dibbashankar's comment. And then there was a question.
I know we are out of time, but I'll just say one small thing to Sharmaji, which is, you know, part of the teleportation protocol is a classical communication part of it. You have to have classical communication as part of teleportation. So it can't be faster than the speed of light. Okay, anyway, go ahead.
And then Umesh Kumar, who is a MSc student, why does quantum entanglement really come into a system? So I think it's a very, it's not very well formulated. What he really wants to understand is what is the meaning of entanglement in something that is easier to understand. That's what he's really asking.
Yeah. Well, I don't know if I'm happy to chat more on email and so on, but I'm not sure I can give you a better example.
Better than the colloquium itself. In some sense, the initial part, the definition part.
Yeah, I think 2 qubits is about as simple as it gets, but okay, maybe someone else has a better.
No, that's fine. That's fine. I think that is okay. And the other aspect to this is essentially thanking everyone, and especially Sandip for this wonderful presentation that excited the community completely. I think we had the largest attendance in colloquium in this online colloquium series. Almost 102 people entered and at one point and listened to the talk. It's also available in YouTube. So all of you, if you want to revisit some ideas, it's very difficult to follow a talk completely. So it's always nice to have a companion, a recorded companion. So YouTube is providing you that option. Just subscribe to the TIFR Platinum Events channel, and you should be able to pull up that talk again and again and listen to bits and parts of this talk. And maybe ask questions in the chat, and maybe Sandip would address some of these. Sandip, it was a very successful exercise for us. Thank you for doing it. And I would like to do a big round of applause if people could actually unmute themselves and give an applause.
Thank you everyone, and thank you especially Jyotishman. It was a great
and I would like to tell all of you before you depart, thank you for sticking around. But the good news, the breaking news is next week we are going to have a colloquium on superconductivity by Anshu Pandey from ISC Bangalore, who is going to talk about his latest results from his lab and how they are trying to understand what they reported almost 2 years back. So, this was a long-awaited colloquium. It almost took 1.5 years to get him here. So I hope all of you can join on the 7th of April. So thank you guys. Thank you
very much.